This is Lisa Schwartz at Berkeley Lab. Welcome to the webinar for the fourth report in the Future Electric Utility Regulation Series. Today, the authors of our new report on distribution system pricing will highlight their findings and take questions from the audience. The series is designed to inform ongoing discussions and decisions by utility regulators, policymakers, and the electric industry. We use a unique point-counterpoint take to present different viewpoints on the future of utility regulation and business models and the trade-off in achieving a reliable, affordable, clean, and flexible power system. The U.S. Department of Energy funds the series. 6 reports are completed or underway so far, and DOE is providing support for an additional series of reports over the next several years. An advisory group of state regulators, utilities, and stakeholders help prioritize what topics we cover and provide guidance on how we cover them. Slide 3 lists our advisory group members, and we thank them. Before I turn over the mic for today's presentation, we have a few housekeeping items. First, we're recording a webinar, and we'll post it on our website for those who couldn't make it today or want to revisit. Second, because of the large number of participants, everyone except presenters are in listen mode only. So please use the chat box to send us your questions and comments. You can enter your questions at any time, and we'll answer as many as we can following the author's presentation. The presentation will take about a half hour, and then I'll moderate Q&A with the authors of the report to answer your questions. Both the report and the webinar slides, and later the recording, are posted at the website shown. Our presenters and authors today are Ryan Hledik, who is a principal of the Brattle Group, where he specializes in the economics of policies and technologies focused on energy consumers. He's worked with clients across 30 states and 8 countries on retail rate design, energy efficiency, demand response, distributed generation, and smart grid. Jim Lazar is Senior Advisor of the Regulatory Assistance Project, where he focuses on utility pricing and resource planning. He has 37 years of experience in 29 states and 11 countries. Among his recent presentations are a primer on U.S. utility regulation, decoupling guides, and reports on retail rate design. Following the presentation by the authors, we'll respond to your questions posted in the chat box. Please enter your questions at any time. Let's begin our presentation. Ryan?
All right, thank you, Lisa. Well, hello everyone. It's a pleasure to be here speaking with you today. This is Ryan Hledik from Brattle's London office, where we are having a quintessentially British summer day where it is 55 degrees and raining. So I hope you are enjoying some nicer summer weather wherever you may be. I'm going to start with the general background on our report, and I will discuss the 4 pricing models that Jim and I have developed in this study. Then I'll present the utilities perspective on the advantages and disadvantages of those 4 pricing models. At that point, I'm going to pass the presentation over to my co-author, Jim, who is going to talk about the consumer's perspective on those 4 distribution system pricing models, so that you can compare and contrast those different viewpoints. And then we're going to conclude with our joint conclusions and recommendations for policymakers in these areas. So as just some general background on our report, as many of you are aware, just by virtue of dialing into this call, adoption of distributed energy resources is growing rapidly across the United States. Batteries are becoming more affordable by the day. Electric water heaters are becoming grid-enabled and able to provide not just conventional demand response load reductions, but also real-time ancillary services. On-site generation, such as rooftop solar, is creating two-way flows on the distribution system. And all of this means that the relationship between the customer and the utility and the power grid is going to change in a way that it really hasn't before. So what this means is that there is the potential for opportunities for DERs to improve the reliability of electric service and to provide some of the distribution services that have previously been provided by the utility. At the same time, it's also possible that DERs will impose additional costs on the distribution system, depending largely on the degree of market penetration. What this ultimately means is that customers, particularly the customers of DERs, may need less than what we're calling a full meal deal from their utility. They may not need to pay for some of the services that they were previously paying for because they're able to supply those themselves, and they may still need other services from the utility. So our report is specifically looking at the pricing implications of these new developments. We set out in the report to do several things. We look at and identify the distribution services that are provided by DER customers to the utility. We look at those services that will still be provided to DER customers by the utility. We then develop several pricing models for pricing and packaging these various distribution services. And we establish some principles for evaluating the merits and advantages and disadvantages of these different pricing models. Finally, the report concludes with some key next steps for policymakers and rate makers to move forward in this area. Now, the report is about 100 pages long, and that's actually the short version. We spent a lot of time editing it and whittling it down to just 100 pages. So rather than walk line through the entire contents of the report, what we're really trying to do with this presentation is to really focus on the discussion on those 4 pricing models that I mentioned earlier that we've developed, and to get into some of the advantages and disadvantages of those. So that will be the specific focus of this presentation. Before we get into it, just a few notes about the scope. The scope of our study is focused specifically on the pricing of distribution services. So those do include customer services such as metering and billing. We're assuming that we are already in a potential future state of the world, say 2030 and beyond, where there has been a high market penetration and adoption of distributed energy resources. And we're assuming that the necessary changes in infrastructure to accommodate this new state of the grid have already taken place. So we're basically leapfrogging to a point in time where we have essentially skipped the transition to this new state of the world and are in a world where distributed energy resources have been widely adopted. Out of our scope is the pricing of generation and transmission services. We're focused specifically on distribution services, though there are times when we talk about the interaction of distribution and supply services. We also are not here to comment on the specific cost effectiveness of any individual distributed energy resource. The purpose of our study is to discuss pricing models that promote the efficient adoption of these distributed energy resources, and that's our goal with this study. So I'll spend a couple minutes talking about the 4 pricing models, given that that really is the focus of the rest of the presentation. The first distribution pricing model that we established is what we're referring to as the granular rate. And what we're talking about here is really an overhaul of the existing retail rate. It's a rate that's highly disaggregated and unbundled. It could vary over time. It could potentially vary over location. And all of this is with the goal of better reflecting the actual costs of the distribution system and its management in the rate structure. So basically, customers would face a schedule of prices. They would pay the prices for those services that they use, and they would avoid or even be compensated according to the same schedule of prices for those services that they are providing to the grid. That's the granular rate. The second pricing model we're referring to as the buy-sell arrangement. And with this model, you don't change the existing rate at all. Customers continue to pay a simple bundled price for their use of the distribution system just as they are currently. And they're separately paid for the distribution services that they provide to the utility under a different pricing structure. So a classic example of the buy-sell arrangement is your, say, conventional air conditioning direct load control program, where customers who participate in that program are continuing to buy electricity at the standard retail rate, and they're being paid by the utility for the peak demand reductions that they're providing through participation in that program. That's an example of a buy-sell arrangement. The third model we're referring to as the procurement model. And with this model, the utilities will go out and procure distribution services from non-regulated third parties through an RFP or by hosting an auction to basically buy load reductions or other distribution services that would allow the utility to avoid, say, new investment in the distribution system. The fourth model is what we call DER-specific rates or resource-specific rates. And in this model, you would develop a new rate for a specific class or subclass of customers that have some set of distributed energy resources. Those customers would pay a rate that reflects both the cost of serving customers with those distributed energy resources and also the value that those customers are providing to the grid. It doesn't have to be a complex rate structure. It's just intended to reflect the average net cost of serving those customers, and it could be higher or lower than the existing average rate. That's a very high-level summary in a nutshell of these four pricing models, and we'll get into the details of these more as Jim and I walk through our respective sessions. Before I move into the next part of the presentation, though, I'll just pause and ask, Jim, is there anything that you want to add to the discussion at this point, or should I move on?
No, please. I think you're doing great.
Okay. Great. Then what I'll do next is talk a little bit about the utility perspective on these four pricing models. Before I do that, I'll just give you a quick reminder. Please, if you have any questions, feel free to submit them in the chat box. And Jim and I are both going to do our best to save a lot of time at the end of the presentation to address those questions and hopefully have a lively dialogue. So I'd like to start my discussion of the utility perspective by making the point that there really is no single prototypical utility. Electric utilities are naturally diverse. There are vertically integrated utilities, utilities that own only transmission and distribution, investor-owned utilities, public power, cooperatives, and each of these utilities has a different resource mix, a different mix of customers, different state policy objectives, and a different regulatory environment. All of these factors will play a role in determining the extent to which these various pricing models are applicable to each utility's individual circumstances. So it's really impossible for me to say there is a specific application of each of these pricing models that will work for every utility. That just isn't going to be the case given the diverse nature of the situations that utilities are in. So what I'm attempting to do in the next few slides is to establish one possible vision for the future about how these models could work for utilities based on my experience working with utilities on distribution pricing matters over the past few years. So I'll start this discussion by saying, I think any of these pricing models can work for utilities and their customers. It's really all a question of how they're implemented. So as with many things in life, the devil is in the details, and implementation and the extent to which you move along the spectrum of a more or less complicated or sophisticated model really is what determines how applicable any of these models might be to a given utility's situation. So starting with the granular pricing model, for example, we're talking about with the granular pricing model an overhaul of the retail rate. And so the risk here is overcomplicating the rate structure to a point that customers can't understand or can't cope with. My recommendation, my vision for the granular pricing model is that it apply to all customers and that it modestly increase the granularity in distribution rates for all customers. So on the residential side, for example, this can mean introducing a demand charge. And the idea there is that distribution capacity costs are driven by peak demand, either on the system or on specific location within the distribution system. Those costs aren't driven by energy. So introducing into the rate a charge that is based on a customer's contribution to the peak demand or maximum demand on the system is a way to better align prices with costs, and this offers an opportunity to customers, particularly those customers with distributed energy resources, to reduce their bills if they're able to flatten their load shape in a way that is beneficial to the distribution system. I think Jim has some other perspectives on that, and we'll get to hear his views on that during his presentation. On the commercial and industrial side, for years now we've been offering demand charges, and we've only recently gotten to the point where metering technology has allowed us to offer these rates to residential customers. So this could be one simple way to basically take those more granular rate structures at the C&I level and bring them down to the residential level. On the commercial and industrial side, rates there have historically tended to be more granular, but there may be some opportunities to introduce hourly variation or even sub-hourly variation into the pricing there. Really the key challenge here will be in balancing simplicity and a rate design that customers can understand with an overall improvement in fairness and efficiency of the price signals that customers are seeing. One example of what I would consider to be a granular pricing model that is in practice today is ComEd's residential real-time pricing rate. This is an hourly rate with day-ahead notification for residential customers. It does apply to supply services and not just distribution system pricing, but it is an example of a rate that's out there for residential customers that has more granularity than the typical two-part rate that we see today. With the procurement model, what we're talking about again is utilities going out and procuring distribution services from customers who are able to provide those services. My recommendation here is to establish an RFP-based procurement model that would encourage location-specific adoption of DERs, specifically in those locations of the grid where it is cost-effective for the utility to be procuring services from DERs rather than from, say, building out the system. And that's really a key aspect of this model is that it be well integrated into the distribution utilities distribution resource planning process. And I think that is probably the biggest advantage of this model is that it gives utilities an opportunity to closely align the procurement of these various services with their very detailed distribution planning processes that are underway. That ability to coordinate is a real advantage of the procurement model. But for this to work, I think there needs to be a robust market for aggregators or other basically third-party intermediaries that can go out and work with customers to provide these distribution services. Other than the largest, most sophisticated customers, it's probably unlikely that individual customers are going to be going out and transacting with the utility to provide these services. And I think this creates a real opportunity for these third parties to come in and help customers and work with utilities to provide something that works both for the utility and the customer. An example of this would be a pretty well-known example. It's Con Edison's Brooklyn Queens Demand Management Project. Their Con Ed is anticipating 56 megawatts of load reduction procured from DERs to defer upgrades in substation capacity in the Brooklyn Queens area. I believe at least a portion of those megawatts were procured through an auction process, and that's an example that's out there today of this procurement model at work. The next model is the buy-sell arrangement, and again, what we're talking about here is that customers will continue to pay the rate that they've been paying for their use of the distribution system, and they'll be paid a separate payment for the distribution services that they provide. What I think is the opportunity for a buy-sell arrangement is in basically ensuring that customers that have otherwise been underrepresented have the incentive to adopt DERs and provide these services efficiently. So for example, in the procurement model that I just discussed, if through that procurement process we're only getting participation from large commercial and industrial customers, it might make sense for utility to establish a buy-sell arrangement that would allow the smaller customers, the commercial customers and the residential customers, to participate directly in a program that would also give them an incentive for providing cost-effective distribution services to the grid. one aspect of the buy-sell arrangement is that compensation should be technology neutral and based on avoided costs to some extent. As these programs are developed, they're going to have to cater to the specific operational characteristics of the technologies that are being adopted in the service territory. But to the extent possible, it's ideal if these programs can be designed in a way that doesn't create a bias or preference for one technology over another and is instead technology neutral. Con Edison's DLRP program is a good example of a buy-sell arrangement. This is basically a demand response program with commercial and industrial customers in their service territory where customers are paid, I believe, at least 2 times the standard incentive payment to participate if they're located in certain parts of the distribution system where those demand reductions are the most valuable. So that program is a good example not only of a buy-sell arrangement, but also of a locational compensation policy, which can be really important from the perspective of managing the distribution system. So the last model, the DER specific rates model, again here we're talking about developing new rates for subclasses of customers that have specific DER technologies. My recommendation with this model is to limit the DER specific rates to important, unique applications. And what I mean by that are those applications that have the potential for large participation and or significant impacts on the distribution system. So for example, electric vehicles have the potential for high levels of adoption and could significantly impact the distribution system if customers are all coming home at around the same time and plugging their vehicles into high-speed chargers that dramatically increase load. In that instance, it can make sense to develop, as many utilities have, an EV-specific rate that would encourage charging during off-peak hours or encourage smart charging to stagger load on a given circuit. Now, whether these rates would be mandatory or voluntary will clearly depend on the policy objectives of each jurisdiction. One recent example of DER-specific rates is Salt River Project's Customer Generation Price Plan, where they've introduced 3-part rates with a demand charge for new residential customers with distributed generation. And we've seen several other similar proposals to this recently, where a new rate has been developed specifically for a class of customers with distributed energy resources and a different cost to serve than the rest of the residential customer segment. So those are the 4 pricing models. I've also included a slide here on key considerations in the transition from the utility's perspective. In the interest of time, I won't walk through each of these, but as you can see, there are a number of considerations that are going to determine the degree of complexity in the implementation of these models that should be tolerated or really pursued. And really what it all boils down to is it worth the effort? And what I mean by that is, I think it's clear that with the adoption of DERs, change will be needed and new pricing models will be needed. The question is where you end up on that spectrum of very complex pricing models versus perhaps more blunt but also less costly pricing models. And what needs to be done is an assessment of really the dollars that are at stake here. What is the magnitude of potential customer bill savings that we're seeing with the adoption of DERs on the distribution system? And what is the potential magnitude of cost savings? And there are probably going to be some utilities that are projecting very significant growth in distribution costs over the next several years, and maybe at the same time projecting significant growth in adoption of distributed energy resources. That would be an example where it probably would make sense to pursue some of these more sophisticated pricing models. At the other end of the spectrum, simpler models might get the job done. So it's really a question, going back to the point that I made at the very beginning of the presentation, I really see this as being a utility-specific thing that will require a lot of analysis and careful thinking at the individual utility level. So I will stop there and pass things over to my co-author, Jim Lazar, but I am looking forward to taking any questions at the end of the session. Thank you.
Thanks very much, Ryan. You've done a terrific job lucky to have Ryan do the heavy lifting of explaining these pricing models. I'm going to be talking primarily about consumer perspectives on this, consumer and ratepayer perspectives on all of this, because the consumer is in a different role with DERs in their relationship with the utility and the utility system. And we're going to need some adaptation, but there's going to be some things that I think will work and some that won't. I'm starting with three guiding principles. The first is that whoever's in charge, whoever controls a DER function, should bear the economic consequences. Second is that whoever's in control of a DER should be presented by the utility grid, the utility regulator, with appropriate economic opportunities so that efficient choices can be made. And the third is that the owner of a DER, who may not be controlling it, may have signed control over to somebody else, but the owner should be appropriately compensated when another party uses that DER for somebody's benefit other than the owner's benefit. So if my Tesla Powerwall gets used for some purpose other than my home, I should be compensated. So I think it's important to get a sense of the kinds of DERs that individual consumers are likely to own. And I've put some pictures here of a grid-integrated water heater with a control box that communicates, a smart thermostat that can respond to prices and to external controls, a home backup generator that can bring 12 kW of capacity on an as-needed basis, a Tesla Powerwall home battery system, and a photovoltaic system. These are examples of the kinds of DERs that customers are likely to own. And it's important to think of some of the services these can provide. This is a graphic from Stethus Corporation of how they can use grid-integrated water heaters, that is second-by-second control of electric resistance water heaters, to follow the PJM frequency regulation signal. If the grid slows down, they take load away so it can speed up. If the grid speeds up, they add load so it slows down. The red line is the frequency regulation signal. The blue line is the water heater consumption. Obviously, an individual consumer can't do this themselves, but aggregated through a provider, they can provide very economical, fast regulation service to the utility. Another service that the water heater can provide is diurnal storage and load shifting. The red line shows when the water heater is being charged, either in the middle of the day on a solar-heavy system or the middle of the night on a system that has excess power in the evening hours. The blue line below that shows the actual water heater consumption, the hot water consumption of the household. And down below, the green line shows the customer's never running out of hot water. So the customer's hot water needs are being met. And then the inset is providing fast regulation service. So here the water heater is providing diurnal storage, load shifting, peak load reduction, off-peak load augmentation, and fast regulation, all out of their residential water heater. They can provide dispatchable capacity. Clearly a home battery or commercial battery or my hospital's uninterruptible power supply battery bank for its surgical suites can provide dispatchable capacity when that capacity isn't needed for the customer's own purposes. So that's another service that folks can provide. I want to get into the granular rate setting. I think this is probably the place that Ryan and I have the biggest disagreement as to what is practical. I think we agree that it's theoretically workable. He talked about adding demand charges to residential customers. And in the paper, in my section on the consumer perspective, I present the Garfield and Lovejoy criteria for evaluating the efficacy of system capacity cost recovery. And there's 7 primary criteria they use, A coincident peak demand charge meets 3 of those criteria. A non-coincident peak demand charge meets 1 of those criteria. A time of use energy rate meets all 7 of them. So I'm a little hesitant to agree with Ryan that demand charges for small use customers, small commercial and residential, are a pragmatic option. And this table is taken directly out of the paper. This is the illustrative granular rate charging for capacity and capacity for various things, power quality and reliability services, other services, all on a granular rate. First of all, while Ryan and I have done cost allocation studies for utilities, there are hundreds of ways to do them. There's little agreement on the best methods. Utility regulators often accept none of the methods, and getting all the way to a granular rate would first lead to the consultant tearing their hair out, then to the regulator tearing their hair out, and ultimately, when this bill gets to my mother, I have a sneaky feeling that $33.53 is the only part of the bill that she's going to understand or be able to respond to. The buy-sell alternative, on the other hand, I think is very workable, where the customer would pay the ordinary rate for ordinary power service, and if they happen to have a grid integrated water heater, that the utility can buy back capacity services or power quality services from and give them an explicit credit on their bill. I think that can work for consumers. And this is an example of that out of the paper. The buy-sell address, in my opinion, the buy-sell mechanism addresses a lot of concerns that many utilities and their regulators have with net metering. Here, I've presented sort of a solar advocate's view of net metering. The utility loses the retail revenue, but it gains it benefits from long-run avoided costs for generation, transmission, distribution, reduced emissions, avoided risk, local economic development benefits to the community. It avoids future carbon costs. There's shading benefits that reduce air conditioning load, and many, many more benefits. And solar advocates think net metering, if anything, is not generous enough. Utilities tend to look at it the other way. They see the lost revenues from net metering at the retail rate significantly outweighing the short-run fuel and purchase power costs, and thereby leaving utility system costs that need to either be recovered from other non-solar consumers or absorbed by the utility, and that's not perceived as fair. In a value of solar approach, the buy-sell approach that, for example, Austin, Texas uses, the utility's average cost of service is reflected in the retail rate. The customer price for solar production is based on long-run avoided costs for the direct economic benefits that the utility system receives, and based on the studies done in Texas and Minnesota and in Maine. In most jurisdictions, and not all, but in most jurisdictions, those long-run costs are on the same order of magnitude as the utility average cost of service, about 10, 12, 13 cents a kilowatt hour. Different in low-cost and high-cost jurisdictions, but for most of the jurisdictions, it works out pretty well. By happenstance, that is, the net metering happens to approximate a value of solar approach. But under buy-sell, a true value of solar approach would quantify that more accurately. The procurement model is one that I'm particularly attracted to, where the customer would be shopping for a new water heater, and they would get to Home Depot, and if they chose the grid-integrated water heater, they'd get a $200 discount on the water heater. So instead of paying $400 up front, they'd pay $200 up front, and that will attract them to the program. Once they enroll the program in the control program, they get a $10 a month credit on their bill. and every time they push the red button to override the system, because everybody's at the, all the kids and grandkids are at the house, they pay $1 a day to override the utility curtailment. Turns out those overrides are very, very infrequent and most often happen on days like Thanksgiving and Christmas when the grid is generally not very stressed anyway. Resource-specific rates can work. We have an example in the paper of a resource-specific rate for a grid-integrated water heater where you start with the standard residential rate. The customer with uncontrolled water heating would actually pay a higher rate. The customer with controlled water heating would pay a lower rate. So the customer that does not have an electric water heater would pay one rate. That with a uncontrolled would pay a higher rate, and with a controlled water heater would pay a lower rate. It can work, and in fact it does work. There are utilities that already have these kinds of rates. Here's an electric cooperative energy-wise rate, which has a seasonal energy price and then a separate lower rate for off-peak space heating and off-peak water heating, and a different lower rate for 8-hour interruptible water heating and for cycled air conditioning. So the resource-specific rates are with us. They can work. Pretty clear customers probably can understand them and respond to them. What I think is probably the most important thing to remember about this paper is we are only talking about the distribution system pricing and distribution system benefits of distributed energy resources. Most DERs have upstream impacts, and the benefits on the power supply side may dwarf the benefits on the distribution side. The environmental and health benefits of DERs are significant on the power system side, may be trivial or meaningless on the distribution system side of the equation. We don't touch power supply impacts, but they certainly, in the paper, it's beyond the scope of the paper, but they certainly can't be ignored. There's really three elements to a vision for the future that I draw out of this paper from a consumer perspective. First of all, one of universal service. The customers ought to be able to connect to the grid for basic service for no more than the cost of connecting to the grid. The cost of the grid itself, the poles, the wires, the substations, need to be recovered based on how much customers use the grid on some kind of usage basis. Second, that prices need to be time varying. Customers should pay for grid services and frankly also for power supply in proportion to how much they use and when they use it. And the third is fair compensation. Customers supplying power and other services to the grid should be compensated fairly for the value they provide, whether it's a smart inverter providing voltage support or frequency regulation services, or a grid integrated water heater providing peak load relief and fast regulation. The customer there needs to be some framework for fair compensation. I'm going to touch very quickly on our conclusions in the paper. Most important is this is a nascent science. We're beginning to understand what services can be provided. We're beginning to understand how to measure and value them. We're beginning to understand how consumers can respond. But we've got to gather stakeholder input from the industry that provides measures, from the industry that can provide aggregation, from consumers, and from utilities. We've got to do some pretty serious market research and see what customers do respond to. We've got to come up with some ways of quantifying value. There's not a lot of consistency in how it's being done around the country today, as evidenced by the different results we're seeing on solar valuation. We've got to implement some pricing pilots. So there's actually some pretty good examples out there. We've shown a couple of them in the paper utilities that are actually doing some pretty creative things. Now the pricing pilots are going to need to have. We've got to assess the power supply impacts. I mean, we can't look at the distribution costs in a void. And there may be measures that add distribution costs but provide huge power supply benefits, and there may be measures that go the other way. And we need to kind of identify, what are the categories of distribution services and power supply ancillary services that can be most economically provided with DERs. I think there are quite a few. Gauging consumer acceptance and response is going to be key here. If we do a good job, everybody's happy. If not, it's not a pretty picture. So in terms of the pilot programs, we think we need to test multiple concepts, probably test all 4 models. I would think that the granular pricing model would be best tested with large volume customers and some of the others with residential and smaller commercial customers. We should seek compatible service territories to test these concepts so that we're testing the same concept in similar service territories to see how similar customers respond to different programs. They've got to be geographically separated enough that they're not seeing the same marketing material and advertising. And then we've got to measure customers' response to those programs that are opt-in, that are default in with an opt-out, and those that are mandatory. The results that we've seen so far suggest that the default and mandatory options produce the most response, but do they produce the most customer satisfaction? There's some services that I think are going to be best provided by DERs. The smart inverters, I think, are going to be the tool for voltage support. I think water heaters are going to be the best tool for fast regulation and diurnal storage. There's going to be a role for federal coordination of this research if for no other reason than that part of this, I think, will need to be development of appliance standards so that the water heater you buy at Home Depot is ready to communicate with the utility to provide distribution services. There's going to be significant differences across geographic areas. The southern states and the Pacific Northwest and Hawaii, to the extent that it's not very big, but it matters certainly, have very high electric water heating penetration. California, the Northeast, and the Midwest have much lower water heating penetration. So some of the analysis is going to have to be geographic in scope in order to find good results. And with that, I think we're ready to take on all of your questions. And we'll be here for a while to do that.
Thanks, Jim and Ryan. This is Lisa Schwartz with Berkeley Lab. We've had a host of questions in the chat box. It's not too late to add yours. Let's start with a question from a member of our advisory group. Commissioner Lang is noting that avoided costs here seem to be redefined to compensate for when and where. And that's really a departure from how avoided costs are traditionally defined. Could you comment on that?
I'll take a stab, and I'm interested in Ryan's response also. The avoided cost that was historically calculated under PURPA was an avoided cost that would be paid to a large utility scale or industrial cogeneration scale power supplier delivering power to the system at the transmission level in competition with utility-owned generation. And it wasn't calculated to be a delivered power price. And clearly for distributed resources, we're avoiding, we hope, transmission and distribution costs as well as avoiding or modifying power supply costs. So it is indeed a different measure of avoided costs than the traditional one.
Yeah, and just to add to that, I think what we're talking about doing here is calculating the same type of avoided cost, but doing it on a more granular level. So to use a demand response example, most utility demand response programs today are designed to encourage customers to reduce their consumption during the hours of the system peak. And they're designed to avoid generation capacity costs and maybe some transmission costs at the system level. So when that's the type of cost that you're trying to avoid, it doesn't really matter where you are located on the system, because everyone's load reductions help from that standpoint to a certain extent. When we're talking specifically about distribution services, location starts to matter a lot more. And avoiding distribution system costs really does have a locational element to it, and then also definitely a temporal element to it as well. And so when we talk about distribution services, getting down to that level of granularity really, I think, is important if you really want to accurately reflect the cost that you're avoiding through adoption of DERs that can provide these various services. So that's why we're talking about introducing that level of granularity here, when it's not something that historically has been part of the conversation as much.
So what are some of the penalties in the FEUR models for non-performance by the customer?
That's a great question, because I think, from the utility standpoint, the dependability and the reliability of the services that are being offered by the DERs is important. I guess if I were to look at that from the perspective of with respect to the granular pricing model, there, if this model were really implemented, I guess the example I could use is, say, a time of use rate or a demand charge. If customers have DERs that allow them to reduce their consumption during peak hours or during the hours of their maximum demand, then the benefit to the customer with that type of more granular rate design is that they're going to reduce their bill, and if the rate is well designed, they're going to reduce the system costs. If that customer isn't always able to reduce their peak demand, then they are going to end up paying for that peak consumption, whether it's through a time of use rate or through a demand charge. And so at least with that pricing option, it has basically a built-in, I don't know if you'd call it a penalty, but basically a built-in price signal that charges customers for their use of the grid and compensates them by avoiding those prices otherwise. Jim, I don't know if you want to comment on any of the other models, but I think that one was sort of the easiest one to illustrate that example.
I think in the other models, the simple answer is that the customer doesn't deliver, the customer doesn't get compensated. That if you've signed up for you've signed up for a grid integrated water heating program, if you're pushing the override button 10 times a month, you're going to wind up with zero net benefit, even though you're still providing 20 days a month of services to the grid, because you're going to get a $10 credit for participating, but you're going to pay $1 every time you hit the override button. You can wind up actually signing up and then hitting the override button every day and paying $20 a month extra. I don't think that'll happen, but conceivably the grid would be well compensated for anticipating you providing services and then you not delivering those services.
Let's move on to another question. We have a question about the pricing model specifically. Under which of the pricing models you put forward as potential options in the future do you see, Jim, water heater aggregation to be most effective for both maximizing the customer benefits and the utility benefits?
I personally think for water heaters, the procurement model is the attractive one. That you've got some kind of an upfront incentive to get the customer to choose that, to get the installing plumber to say, I can save you $200 if you let me put in the smart water heater, and then you'll save $10 a month if you let it be smart, is going to be very attractive for water heaters, for smart inverters, for smart thermostats, and ultimately, I think, for smart refrigerators and freezers, which will, be controlled by some kind of an aggregator to, in the case of the fridge, to pre-cool and then coast through peak periods. And I think that getting some kind of a lump sum up front for signing up and then some kind of a monthly benefit for staying subscribed is going to be probably the easiest one for small consumers to understand, and by overcoming the first cost issue for them, very attractive.
All right, we have a question about energy efficiency. How can we maintain a strong price signal for overall energy efficiency, not just pricing to affect time of use?
Well, what I think we're talking about with any of these models really is it's not about discouraging energy efficiency, but it's about encouraging the type of energy efficiency that is most valuable to the system. Right now, for the most part, energy efficiency incentives are just based on encouraging overall energy reductions regardless of when those energy reductions are actually occurring. What we're talking about with these models is providing a price signal that not only encourages energy reductions, but encourages them during those hours when they are the most valuable to the grid. So I see these models as providing an incentive for energy efficiency, just maybe to some extent a different type of energy efficiency than we've been getting historically in a lot of cases.
And I'll respond, and Brian may want a little rejoinder on this, that the rate design RAP has addressed repeatedly in our Smart Rate Design paper, that are also addressed in the fixed charge paper in this series, that customers should see substantially all of the cost of electricity in a rate per kilowatt hour that they can avoid, and we believe that should be a time varying rate. And the general tariff will do the most for energy efficiency. The items we've addressed here in providing distribution system services are mostly involved in shaping usage and curtailing usage at key hours to reduce distribution system capacity requirements, and then providing, I'll use the term broadly, ancillary services back to the grid that may be more economically provided by DERs than by power supply, traditional power supply sources. But the key is a time-varying energy rate that customers can understand. But probably most important is a rate design that customers can understand. You can't respond to something.
Yeah. I won't get into the fixed charge issue too much, because I think that's actually going to be the topic of one of the next reports in this series. But I like the way Jim characterized that. I mean, what we're talking about is providing incentives to shape energy efficiency in a way that's most beneficial to the system and customers as a whole.
How do you two see the development of cheaper storage options, particularly solar with storage? How do you see these pricing models addressing that potential future?
Well, cheapest storage is going to be ice storage, air conditioning, and controlled electric water heating. Maybe 1/10 the cost per kilowatt hour of any kind of battery storage. And part of the whole point of the procurement of the procurement model is to come up with a simple way that a large number of small thermal storage devices can be gathered together to provide both the power supply system load shaping service and the distribution system load shifting service.
Yeah, and what I like about the procurement model is, at least as we've envisioned it, the utility could define some service that it needs, whether that's a load reduction on a specific part of the distribution system or some other distribution-related service. They could define the service and then accept, bids or offers to provide that service, regardless of the type of technology that's providing it. And that's what I meant when I used the term technology neutral earlier. So to the extent that a grid-connected water heater can provide those sorts of that sort of load shaping or load shifting versus a battery, it doesn't really matter as long as the utility has a reliable service that it can depend on, and the most cost-effective options in that case are the ones that would presumably be procured.
So how does the granular pricing model work in a world where you have potentially high levels of central station renewable generation, especially wind in some parts of the country, and you have a lot of periods where you have over-generation? How might the granular pricing model help or maybe not help as much?
So I can take a quick stab at that, Jim, and then feel free to add on. I think it's a really good question, and this is actually something that I think Jim and I both struggled with as we first started to scope out and write this paper. We are focused specifically in this study on distribution pricing, but that clearly is only part of the customer's bill. There are all, the transmission, generation-related costs that we mentioned are significant costs, and I think often represent together at least the larger portion of the bill than the distribution system costs. So with any of these models, I think Jim and I both agree that you need to be procuring these distribution services in a way that is coordinated with whatever you're also trying to do to procure supply and avoid, say, transmission costs. And with the granular pricing model, if customers have certain price signals that they're seeing at the distribution level, certain prices that they're seeing at the supply level, finding a way to combine those prices and basically simplify the rate without losing the granularity that you need to provide those price signals is going to be one of the challenges, but I think it's a really important aspect of all this.
All right, there's a question about how do you actually determine these prices? For example, voltage support. How would you go about determining how you'd set the price under these various models?
Well, it's being provided now. It's being provided now by having power plants that are running at less than their maximum capacity that can be ramped, and more than their minimum capacity that can be ramped down and ramped up. It's being provided now with voltage regulators on the distribution system that may cost $75,000 per circuit to install. And so we've got some ways of measuring the avoided costs. And if we can displace the need for a $75,000 voltage regulator by giving 75 PV systems a $1,000 incentive to install a smart inverter, then we've broken even. And if we can do it for less than that, then we're saving money for the non-participant customers.
All right, someone had a question about wholesale markets. And the question is fairly complex, actually. With differing state regulations, how could the development of these state-specific rate structures impact utility and aggregator competitiveness in wholesale markets? I mean, we already have different state regulations today, right?
Sorry, Lisa, could you repeat that question?
Sure. The question is about for competitiveness in wholesale markets. If you've got differing state regulations about how to go about pricing these distribution services, is this going to affect the competitiveness of utilities and aggregators in wholesale markets, having state-specific rate structures? And I guess as a starter, I'd say we already have state-specific retail rate structures.
Yeah, I mean, I think, we see differences at the state level in terms of, opportunities that, say, utilities are offering to aggregators to provide capacity. And I think maybe this kind of goes back to the point that I made earlier about the difference between distribution level services and services at the wholesale level. There is an important coordination aspect there that's going to be, I think, a challenge to address here unless you're able to coordinate this in some way. But that doesn't mean that, you can offer products, programs for aggregators to provide at the distribution level separately from wholesale market opportunities and not necessarily run into issues if they're providing services into either of those markets.
Okay, there's a question about locational differences and how you account for those. How do you account for the locational differences in the amount of the benefit or in the amount of the avoided costs of distributed energy resources?
So that's a good question. I mean, I think going to the example that I had given earlier in my presentation of Con Ed's distribution load relief program. There they have a demand response program that is targeted to their distribution system, and they basically divided their distribution network up into two zones. I forget the terminology, maybe it's zone 1 and zone 2. But they've divided the network up in such a way that they know those portions of the network that are in more of a need, say have more of a short-term need for new capacity. And if you're a customer who's located in those specific locations of the network, then you're offered a higher incentive payment to participate in the demand response program, and you're offered a higher payment for the load reductions that you provide to the system. So I think this requires a study, a distribution level study, like some of the distribution resource plans that utilities in California and New York and Hawaii have been developing, to really look in a way that we probably haven't before at what specific locations of the grid are in need of upgrades, and to develop programs and pricing structures that reflect that new analysis.
All right, Tim, I think this is a question for you. In the granular pricing model, what percentage of residential customers are going to pay attention to and act on day-ahead notification? And I guess I'd add, do they have to, or will that response be automated?
Well, right now there are currently 15,000 customers on ComEd's real-time pricing program, and they receive day-ahead notification, and they seem to be saving money. Part of that is they're avoiding the hedging costs. That is, even if they don't change their behavior, then they save money. But the folks I've talked with and the evaluation I've heard is people do respond. But to the extent it can be automated with smart thermostats, with smart refrigerators, with smart air conditioners, I think that can change quite a bit. But that time varying pricing, I think, would be a logical component of any future rate design, either on a default, mandatory, or opt-in basis. And so all of the other models will also be able to take advantage of it. And in the case of the procurement model, the devices will be compensated. The owners of devices will be compensated for programming the devices in to take advantage of those.
All right, this should be, I think, a quick question to answer. If you've got these resource-specific rates, does the end use specifically have to be sub-metered?
No. You can, figure that the electric water heater is going to use 4,000 kilowatt hours a year, and you can figure out what that works out to in terms of the benefit, and modify the overall rate for the total metered use of the customer, knowing that you're controlling the water heater. But frankly, with today's measurement devices, if you've got the ability to control the water heater, you've got the ability to measure what it's consuming also. Stepless and sequentric systems would give you that information. So you may get to sub-meter, you may get to virtually sub-meter those end uses anyway.
All right. On time varying rates, seniors and people that work from home, may cause energy usage in the household to increase. Should this higher usage be considered as to whether the customers would benefit on these proposed rates? If so, why or why not?
So with time varying rates, you want to design the rate to reflect the cost of the system. So to the extent that a customer's bill would go up as a result of, say, being moved to a time varying rate, that should reflect the cost of their use of the system as opposed to being an artificial bill increase. So it would be fair in that sense, but that said, there's often, in most states, there's typically a policy goal of making sure that vulnerable or low-income customers are protected from the cost of electricity becoming unaffordable. So I think Jim and I have both done work on looking at when you are making this type of rate transition, how you transition to rates in a way that will either ensure that customers like those most vulnerable customers don't see a huge increase in their bill, or that they otherwise get the type of education and information that they need to be aware of the options that they have for responding to this new price structure. And there are a lot of ways, from shadow bills to say subsidies for new automating technologies, a lot of different ways that you can go about doing that. But the point is, I think that as you transition to these new pricing models, having a very clear and well thought out transition and education plan for customers is going to be an important aspect of this.
All right, there's a question about the durability of the price signal, however you want to define that. So the question is, what's your perspective on customer appetite for these kinds of pricing models? Depending on the durability of the price signal, it seems more worth it for a customer to make an investment in a distributed energy resource that might have some value to the utility system if they know that that price signal is going to be there for enough years to pay back the investment. Any comment on that?
Gradualism and predictability and stability are among the important fundamental rate-making principles that Von Bright taught us in 1961. And I think that remains true today, although the world is moving a lot faster than it did in 1961, and we're going to have to be pretty creative, at least offering optional rates and perhaps default rates that change more quickly in form and magnitude than in the past.
All right, here's a question. If I'm spending more to expand a demand response program, let's say I'm paying for demand response from customers, in order to manage the so-called duck curve with solar PV that's pushing peaks into the evening and causing some over and under generation issues and ramping issues. If I'm paying for that, how does that get taken into account in the so-called avoided cost I'm paying for solar customers for energy capacity from their systems?
Well, pricing is going to get at the power supply side of that, but the distribution part of it is a little different because the distribution impacts can be so localized.
All right, and this is a really good question, I think. Is there an economic argument for paying utility customers the same amount for a service from a distributed energy resource system to defer utility investment, the break-even, Jim, that you referred to earlier? Because the ratepayers would have to pay for that in the absence of the ERs, or should they pay just up to?
Right. And there's an argument for paying them what the utility would otherwise incur, and there's an argument for paying them no more than it takes to get the job done. And frankly, if you can get the job done for less than the utility would otherwise have to pay, you ought to have a procurement mechanism or a pricing mechanism or a buy-sell mechanism that attracts enough customers to provide the resource at a lower cost than the utility would otherwise have to pay. And in essence, we've reduced the avoided cost.
Yeah, and that's really one of the main objectives of these pricing models is to give customers and utilities the financial incentive and the price signals that will encourage the provision of these services at costs that are below what we're already seeing utilities have to pay today. This might be a little bit of a tangent, but Lisa, that your question raised an interesting point about paying customers the same price, and that has to do with whether it makes sense for prices to vary locationally, which is something that we've talked about. I think from an economic standpoint, there's an argument to be made for prices differing across locations in the distribution system. From a practical standpoint, something that I think regulators and utilities and stakeholders will have to take into account is that there could be some issues with one customer seeing that they're paying one price and their neighbor paying another price, and customers being confused as to why that might be the case, when to them all the electrons seem to be the same electrons and do the same thing when they turn the lights on. So there are definitely practical considerations that need to be taken into account with locational pricing, and that's the sort of thing that the pilots that we've recommended in our conclusion could help to address.
David actually raised a very important issue here. I mean, there's been some analysis done by Cephas and Sequentric in the Midwest, that the annual cost at wholesale of the electricity used by an electric water heater is under $100. The value of the fast regulation services that water heater can provide can be, $150 or $200 a year. So you wind up actually, if you on a full compensation basis based on the utilities, or the grid operators' willingness to pay for frequency regulation, a negative cost of hot water. Do you need to pay that much, or would people be willing to sign up for something less than that? And that way, all ratepayers, whether they're participants or non-participants, can benefit. I think we need to test that, and it's going to take a lot of experimentation and a lot of evaluation to see what works best.
We have a comment that both of you have had significant international work experience. So can you comment on any similar developments in distribution pricing in other countries?
Oh, I guess my favorite is France. My second favorite would probably be Indonesia. In France, the utility, it's a vertically integrated utility. It offers three rates, basic rate schedules to residential customers, a flat rate, a time of use rate, and a critical peak rate. But for each of them, the customer subscribes to a level of demand. So the rate design winds up being, in essence, $3 a month for the connection, for billing services, plus $1 per kilowatt per month for the connection to the grid, and then either a flat rate, a time of use rate, or a critical peak rate on top of that. They accurately price the customer-specific capacity, and the time of use rate is marketed primarily to customers with electric water heaters that are controlled, and the critical peak pricing rate is primarily marketed to large residential customers, including large residential customers with electric water heaters that are controlled, so that the small customers get a cheap connection and a simple price for a small amount of use, and the medium-sized customers get a little more complicated price with an incentive to give over control of the water heater to the utility, and the large customers see a very granular price.
Yeah, and there's an interesting example here in the UK actually. The UK is kind of at the retail market is structured kind of like Texas, where there's significant retail competition. Customers sign up with the supplier, and they pay whatever rate that supplier decides to offer the customer, and it's not a regulated rate. The retail supplier is facing a very granular price structure. They're paying a distribution charge that has various price signals. They're paying transmission charges that might have demand charges that are based on the system peak. They're going out and procuring generation capacity and energy. But the customer isn't seeing all of that. And the supplier is acting basically as an intermediary that absorbs some of that complexity and passes on a simpler price signal to the customer. There's one retail supplier here, sort of a startup called Tempest Energy, that is actually going in and signing up customers and installing various load control devices on the customer's end uses and appliances and processes, mostly larger commercial and industrial customers. In return for giving Tempest Energy that control over some of their end uses, the customer receives a discount, and Tempest Energy is able to manage that customer's load against all of these different price signals in a way that lowers their cost of serving the customer. So it's sort of this interesting model where you have on one end a very granular price signal. In the middle you have a retail supplier who absorbs all of that. And then they pass on savings to the customer to the extent that they're able to help that customer manage their demand. So I think that's an interesting example that illustrates a lot of the points we've been discussing here.
Well, thank you, Ryan and Jim. We're out of time. Thanks, everyone, for joining us. Our next report up, report number 5, is on recovery of utility fixed costs. And we have 4 perspectives: utility, consumer, environmentalist, and economist. We expect to be releasing that by the end of June. And then in July, please look for a report on the future of resource planning. And DOE has generously offered to continue funding the series, so there'll be additional reports after that. Thanks very much for joining us. Bye.
Thank you.